Hello, year 13s. So I'm going to take you through this next part of our halogenoalkanes topic. So if you turn to page 7 of your notes, I'm just going to go through the preparation of halogenoalkanes with you now. So the first method that we're going to look at is the main method for preparing halogenoalkanes. And it's a method that is long, and you have a long method to learn. But this can quite often come up on the practical exam, particularly the written practical exam, the practical paper B that you will do in the exam hall in June. And so you need to know this really well. But the first thing you need to do is there's a little mistake in your notes. And that is that where it says number 1 here, primary alkanes from primary alcohols. That should say primary halogenoalkanes. So that should say primary halogenoalkanes from primary alcohols, because after all, that's what we are trying to make, halogenoalkanes. So the first and main method we use for preparing halogenoalkanes is by taking the corresponding alcohol. So say, for example, we want bromoethane. Then we would take ethanol. So we take our corresponding alcohol and we react it with hydrogen bromide, HBr. Okay, and we're going to focus particularly on the preparation of 1-bromobutane, as it says here. And this is the preparation that you should learn off. Okay, and as we said above, we are reacting our alcohol, so our corresponding alcohol. If we want to make bromobutane, then the alcohol we want to be working with is butanol. And it's butanol because we need it to be a primary alcohol, as it says up at the top here. Okay, and primary alcohols are just named in the same way as our primary, secondary and tertiary halogenoalkanes. So butanol has this structure. If you can imagine, all of those dashes have hydrogens at the end. I'll just draw them for our central carbon. As you can see, it's only connected to one other carbon atom. The other bonds are bonded to 2 hydrogens. And so because it's only bonded to one other carbon atom, then we call this a primary alcohol. Just in the same way as we named the structure of our halogenoalkanes. Okay, so that's what we're working with first of all, is butanol. Okay, and that's the corresponding alcohol because we want to make bromobutane. Okay, now we said the other thing that we need to react it with is hydrogen bromide. Okay, and hydrogen bromide, we can't just add hydrogen bromide directly. And that's what this part here means about in situ. And in situ just means that rather than adding hydrogen bromide directly, hydrogen bromide itself is kind of made in the reaction mixture before it then goes on to react with our butanol. Okay, so there's 2 reactants that we make our hydrogen bromide from. Those 2 reactants are concentrated sulfuric acid and sodium bromide. Okay, so what they do, first of all, is they react together to give us our hydrogen bromide. So we've got sodium bromide reacting with sulfuric acid to give us hydrogen bromide and sodium hydrogen sulfate. Okay, now that we've got our reactant, the one that we want, our hydrogen bromide, it will then go on to react with our butanol. So butanol is C4H9OH plus our hydrogen bromide gives us 1 bromobutane plus water. Okay, so you can see we're swapping our alcohol group with the bromide ion. Okay, so the bromide ion is moving in, and then the alcohol group of the butanol reacts with this other hydrogen from hydrogen bromide, and that gives us our water at the end. Now, our overall equation is just written by adding these two equations together from step 1 and step 2. And we can do this by just adding up the left-hand side and adding up the right-hand side. But we can see that there's something that's going to appear on both sides of the equation when we add them together, and that's our hydrogen bromide. So we can cross that out here and cross that out here. If it helps you to see it better, then add up both sides of the equation, write them out, and then you'll see that hydrogen bromide appears on both sides, and so you can take that out. And so your overall equation is your butanol plus your two reactants that make the hydrogen bromide. So our sodium bromide and sulfuric acid, and they go on to make our bromobutane plus, as our side products, water and sodium hydrogen sulfate. If you can, try and fit those all in the one line. So make sure you've copied those into your notes. Okay, if you haven't already done that, if you pause the video, because I'm going to rub out that last equation, or part of it anyway, so that I can write this next part of the equation. What we find when we do this reaction is that some of our hydrogen bromide oxidizes as well. Okay, and it oxidizes, if you remember, oxidation can be three things. So I'll write it up in the corner here. Oxidation is gain of oxygen, loss of hydrogen, and loss of electrons. So what we're going to find with our hydrogen bromide is that it loses its hydrogen and it forms bromine gas instead. And so we've got our hydrogen bromide, and it reacts with the concentrated sulfuric acid, which oxidizes the hydrogen bromide to bromine. So you can see it's lost hydrogen, and that also gives off sulfur dioxide and water. So that's a reaction that we don't want happening, but it happens just as a consequence of the reaction conditions. And the important thing about the reaction conditions is that we start by refluxing. Okay, we reflux a mixture of our three reactants, our butanol, our concentrated sulfuric acid, and our sodium bromide. Okay, and refluxing, as we'll see a diagram of it on the next page. It's, as it says here, continuous boiling and condensing of a reaction mixture. So the reaction boils and then condenses. Okay, we'll come back to that in a second. Now, just as I said earlier, it's really important that you know these steps. There's going to be 13 steps, and they're quite detailed. but you yourself will have to work out a way to condense that down and learn it off. But you need to know these points of preparation, the method of preparation, but you also need to know why each step is done. Okay, so as I said, we're looking at the example of 1-bromobutane from butane 1-ol. So let's have a look at this next page, page 8. Okay, and you can see, just to chat you briefly through here, here's the first 4 points. Okay, so in bold, you have the step. Okay, so there's step number 1, here's step number 2. Then in italics and plain type, we have the reason why we do each of these steps. Now each step has a reason, apart from step number 1. So that means you've got 13 steps and 12 reasons to learn. And it's really important that you do that. Okay, so taking you back to, this is your diagram of reflux. Okay, and you can see that it's fitted with a reflux condenser, which is basically like your Liebig condenser. But it is positioned vertically rather than the way it would normally be in distillation apparatus, which we will also see later on. So the reason we need to use this is because organic compounds, they tend to be quite unreactive, and so we need to heat them in order to get them to react. But then the problem is that they are quite volatile. So they are volatile. What volatile just means is they evaporate off easily. They have quite low boiling points, and so they evaporate off easily. So the reason we can't just heat it over a Bunsen burner or in a water bath is that once our organic compounds get to a certain temperature, they'll just boil off, and we'll lose them. They'll escape as a gas, and so we won't get them reacting. We need to heat it to get them to react, but we don't want them to escape as gases. So what this reflux condenser is, just as in the distillation apparatus, the water running around the outside of the condenser, so the water in here and the water out here. Remember, it always goes against gravity, so water in at the bottom, water out at the top. That keeps the reflux condenser nice and cold, so that when our organic compounds do boil off, they'll condense back down and fall back down into the reaction mixture here and go on reacting. Okay, so reflux is continuous boiling followed by condensing. Okay, so the first few steps are pretty simple. Basically, step number 1 is put all your reactants together in your reacting flask, which in this case is a pear-shaped flask, which is just the name of this piece of apparatus that we want to use for this reaction. So our pear-shaped flask currently contains 2 of our reactants, butane 1-ol and sodium bromide, and also some water as well. The only reactant that is missing is our concentrated sulfuric acid, which you can see is up at the top here. Okay, now you can see step number 2 says place a reflux condenser, we've pointed that out, and a still head. And that's this piece of apparatus here, and you can see that it has an opening here. What that means is that it maintains, as it says down here, an open system. Okay, so we've got sort of gas, air coming in and air able to leave. And that's really important for this. Otherwise it would explode. And so that's why the still head is there, to allow that circulation of gas. Okay, and then our dropping funnel is at the top, and that allows us to add the concentrated sulfuric acid slowly. And that is step number 3. You can see that here, that we want to add our sulfuric acid very, very slowly, drop-wise, through the dropping funnel. But why do we want to do that? Why can't we just put it straight into the pear-shaped flask along with our other 2 reactants? Well, the reason is there underneath step number 3. This is a highly exothermic reaction, and if we were to add the sulfuric acid all at once, it would get too hot, and cause the alcohol to dehydrate. So it would lose water, and we would just see carbon being formed as black flakes at the bottom of the flask. So we can know if we have added the concentrated sulfuric acid too quickly if we see these black flakes of carbon. So, for example, that could be a question on your exam paper. You might be asked to explain the formation of black flakes at the bottom of your flask at this stage, and you may be asked for a way to prevent that. So you could say the black flakes appear because the concentrated sulfuric acid was added too quickly, which resulted in the dehydration of the alcohol. And the way you could prevent that is by adding it more slowly. Okay, the next step number 4 and 5, go hand in hand. And step number 4 says remove the dropping funnel, so remove this piece of apparatus, and add anti-bumping granules. Anti-bumping granules are just small pieces of solids, and what they do, again, looking at your reason here, is they promote smooth boiling. So they prevent the reaction from being too vigorous and too bubbly, and it boils more smoothly. And that just prevents the reactants from splashing around the side of the container and allowing all the reactants to mix and react as far as possible. Okay, and then step number 5 is to heat under reflux for 30 minutes. Okay, so a heat is applied below the pear-shaped flask. And here in your notes, it just gives you reason as to why we need to do this. So as we discussed a little bit earlier, organic reactions or compounds are quite unreactive. And so we need to heat them to get them going. But organic compounds are volatile and would escape off as gas if they were heated. And so we need to reflux it, which, as we talked about, is continuous boiling or evaporation followed by condensation. It means we don't lose any of our reactant or product. Again, the condenser must be open at the top, and that's to, again, maintain our open system. So the next stage in our reaction, which has the purpose of preparing 1-bromobutane, is to use distillation. And the purpose of distillation is to remove our 1-bromobutane, or as much of it as we have produced. So instead of having our reflux condenser vertically, you can see we've now switched it around to the normal distillation position. So we'll heat our reaction mixture, and the hope is that our 1-bromobutane will evaporate off and then condense over to and be collected in the measuring cylinder, which you can see is shown there. Now the problem is that some water will also pass over with the 1-bromobutane along with some other impurities. Some of those impurities are listed here, and I've written the step 1 and the step 2 equations up here to help you picture what sort of impurities you've got there. So you've got water, so there's your water there, but also we added water to the original reaction mixture, so some of that water could be present as well. We've got our unreacted butanol, okay, so our unreacted butanol, sulfuric acid, that was one of our reactants as well, and hydrogen bromide, which as you remember is one of our reactants, but it's made in situ. So some of those impurities may also come over with our 1-bromobutane distillate. So the next steps from this is trying to get, we've made our 1-bromobutane. We make that in the step of refluxing for 30 minutes. But the next stages are just trying to get the pure 1-bromobutane out of the mixture. Okay, so step number 7, we need to separate our distillate. So as you can remember from our properties of our halogenoalkanes, they don't dissolve in water. And so if we think of water as being one of our impurities, water's one of our impurities, then our distillate's going to have 2 layers, because it'll have our organic product, our bromobutane, but also water and the other substances that dissolve in it, like sulfuric acid and hydrogen bromide. Okay, so as you can see here, we've got a separating funnel, which hopefully you remember from GCSE. And we use a separating funnel when to separate 2 immiscible liquids. So 2 immiscible liquids. That means liquids that don't mix. Okay, so we can see that in our separating funnel we have our 2 layers. The more dense layer sits on the bottom, and the less dense layer sits on the top. Okay, now we can do that in 2 ways, as we talked about our density values. So the first way is looking up the density value of the halogenoalkane, and if it is less dense than water, so if it has a density that is lower than 1, then it's going to be the top layer, because it's lighter, it's less dense, than water. But if its density value is greater than 1, then it is going to be more dense than water, and so it sits on the bottom. Second way we can do this, which is in practice what scientists would do just to double check, is to add a small quantity of deionized water to the separating funnel and look to see which layer gets bigger. Okay, so obviously the water is going to go into your aqueous layer, and so that's the layer that you don't want. Remember, we want to keep the organic layer, the layer that contains our organic compound of 1-bromobutane. So think about it as an aqueous layer, which will have our water and our sulfuric acid and our hydrogen bromide, and then our organic layer, which has the product that we want. So we want to get our organic product. So more than likely, as we looked at, halogenoalkanes tend to be more dense than alkanes and more dense than water, and so more than likely it'll be our bottom layer. So the tap will be opened and the organic layer will be run off, and it's important to remember that we don't have a stopper on top of the separating funnel when we are separating, and we'll look at that in a second. Okay, step number 8 we include because the organic product that we've separated off, the organic layer that we've separated off from the separating funnel, is still not pure. So we want to put it into another separating funnel, and we want to add concentrated hydrochloric acid. Okay, we'll talk about that, why we do that in a second. The next step is important to include that we stopper the separating funnel and we shake it in order to mix it. Okay, obviously it's important to put the stopper in so that when we shake it we don't lose any of our product. And we do that by a process of inversion. Okay, so we turn the separating funnel upside down continuously, and every so often it's important to open the tap. And that is important to release any gas pressure. But it's important to open the tap when it's upside down so that our liquids don't run out. So when you've got it inverted, when you've got it upside down, then open the tap every now and again to release your gas pressure. Now the reason we add concentrated hydrochloric acid is to remove the butene-1-ol impurities. So obviously butene-1-ol is going to be part of the organic layer, it's an organic compound. And what the concentrated hydrochloric acid does is convert it to a more soluble ionic form. Okay, so if it's more soluble, more ionic, then it's going to go into the aqueous layer, the layer with the water and the other impurities. And so it moves into the aqueous layer, and then we can separate it off again, which we'll look at in the next step. Okay, over on to page 10 now, and we'll look at our final steps of how we are purifying our product of 1-bromobutane. So we've just added concentrated hydrochloric acid. We've been shaking our separating funnel in order to make sure they're thoroughly mixed and the concentrated hydrochloric acid is able to react with all the butanol. And so now we need to put it in a clamp in order to leave the separating funnel to allow the layers to separate. So we're allowing the layers to separate. So if you think about when you're separating oil and water, you mix them up and it takes a while for the two layers to settle. They will settle eventually because they don't mix, they're immiscible, but we need to give them time to allow those layers to separate. Again, this step is really, really important to remove the stopper. So you had the stopper on to prevent any liquid from being lost when you were shaking and inverting. But if you don't open the stopper, if you don't open the stopper, then you'll have a closed system. So the reasons down here, you'll have a closed system and none of your layers will run out. So if you were doing this practically in the lab, you would notice that if you had your stopper on, nothing would be happening, and you would remove your stopper. But in a practical exam, you won't be doing this in the written exam, and so you need to remember that step. You need to remember to write that. And we allow our lower layer is our organic layer, and we run that off into a beaker. And we want to close the tap, and this is sort of a professional practical note, that close the tap when the junction of the two layers reaches the hole in the tap. So basically just before the aqueous layer starts to run into the beaker, then you stop it. Okay, so you will lose a little tiny bit of your organic product, but that is seen as better than further contaminating your product by adding a little bit of the aqueous layer. After all, the whole point of these final steps is to purify our product. So even if we lose a little bit, it's better than letting some of that aqueous layer in. Okay, now bearing in mind we will still have some impurities, so we need to go on and do some other purification steps. But hopefully now that last step will have got rid of the butanol, the unreacted butanol impurities. Okay, so the next thing we need to do is to remove the acidic purities. So if you think about the acidic impurities, they were hydrogen bromide and sulfuric acid. So both of those are acids. So think about what you might want to use to get rid of those acidic impurities, and that is by adding an alkali. So what we use is sodium hydrogen carbonate solution, which is an alkali, obviously, and will neutralise our acidic impurities. Again, we do this in the same way by placing it into the separating funnel, clean separating funnel. We don't want to add it into the old separating funnel and get our impurities from the last step. And put it in a clean separating funnel. Add our sodium hydrogen carbonate. Just a little note on that. This wash idea, it doesn't mean wash like with soap. It just means add your sodium hydrogen carbonate and mix it thoroughly with your organic layer. What you're trying to do is you're trying to wash out your acidic impurities. So again, invert it, shake it, but release your gas pressure as before by opening the tap when it is inverted. Okay, the reason that is, if you think of when a metal hydrogen carbonate reacts with an acid, we get a salt, water, and carbon dioxide. So carbon dioxide gas is given off, and we need to release that to prevent the pressure from building up in our separating funnel. Okay, moving on then. We've now got rid of our butanol impurities, our hydrogen bromide impurities, and our sulfuric acid impurities. And I should have mentioned above that obviously once we've added our sodium hydrogen carbonate, that means the hydrogen bromide and the sulfuric acid will form an aqueous layer as before, and so we need to separate that and discard the upper aqueous layer. So again, we're running off the bottom layer. Again, stop it just before the junction of where the two layers meet. And then collect your organic layer, and then we'll get rid of our upper aqueous layer. Okay, so the last few steps, we're getting close to the end, but it says our organic layer, the 1-bromobutane, will be cloudy at this stage because we've still got water in it. Okay, so we've got rid of most of our impurities, but we've still got water in it. So what we want to do is add like a desiccant, something that's going to get rid of our water. And so something we can use is anhydrous sodium sulfate, and that is going to get rid of our water. We don't want to add too much, but we can add a little bit, and that will absorb our water, get rid of that. And we add it just in small amounts until the 1-bromobutane is clear. So our final product should be a clear liquid. And so we add our desiccant until it gets to that stage. So again, your reason is there. It's cloudy because of water, and so we add our drying agent to get rid of the water. Anhydrous sodium sulfate is a powder, and so when we've added it, we need to get rid of it. And rather than do that with a separating funnel, because it's a solid, we need to use either filtration or decanting to get rid of the anhydrous sodium sulfate. Filtering, you'll know what that is. And obviously we're collecting our filtrate, but decanting, if you're not aware of, it's basically just allowing your anhydrous sodium sulfate to settle at the bottom and then gently pouring off your liquid, without allowing the solid to flow through as well. So if you think of, let me think, like a cup of coffee with coffee granules at the bottom, and say you want to put them in a clean mug and not get your coffee granules at the bottom, you'd allow your coffee granules to settle at the bottom and then gently pour from one mug to another without allowing the coffee granules to pass into your new clean mug. Okay, and then we're nearly there. The last step is to use our distillation again to collect our 1-bromobutane, and its boiling point is 102, and the more pure our product is, the narrower the range of distillation temperatures. So if it happens at exactly 102 degrees C, it'll be really pure, but more than likely it'll be between about 101 and 103 degrees C. But as it says here, we want a maximum of 1 degree C on either side, if it's going to be as pure as we will want it to be. If not, you'll probably have to go back and do all the purification steps again. But you can see here, because the boiling point of bromobutane is 102, it's very close to the boiling point of water, which is obviously 100 degrees C. So back at stage 6, we talked about how some water would pass through to the distillate as well, and you can see now why that was so, because the boiling point of 1-bromobutane and of water is very, very similar and very close. And so that's why some of our water would have distilled off at the same temperature as well. So there you go. That's your main method for preparing 1-bromobutane. Okay, so that last preparation method was your major preparation method for preparation. Don't know how many times you can say preparation in one sentence. That's the major method you use to prepare halogenoalkanes. There you go, just once. But now we need to look at a few other ways of preparing them, but they're not so commonly used in the lab. And you'll be glad to know that you don't have to know practical details for these remaining methods, but there are another 5 that we need to learn. Some of them we've already met in previous topics, but let's have a look at a couple here. Now, the first one is by, again, taking your corresponding alcohol. So we'll look again, just to keep it the same, about the method of making 1-bromobutane from butane 1-ol, so from the corresponding alcohol, and adding a mixture of PBr5, so phosphorus pentabromide. Okay, we looked in the halogens topic at phosphorus pentachloride, but now this is just pentabromide. Obviously, the Br, we need to use phosphorus pentabromide to get bromobutane. So the equation of our reaction is our butane 1-ol, which is C4H9OH, plus our phosphorus pentabromide, and that gives us our bromobutane, obviously our desired product, and then our side products are hydrogen bromide, and then what's left, which is POBr3. That should be a 3. Okay, under your observations section, it's just a couple of observations. First of all, that phosphorus pentabromide is a yellow solid. Don't know why I wrote it in pink when it's yellow, but there you go. Phosphorus pentabromide is a yellow solid, and when this reaction happens, we see heat being given off, and then if you remember again from our halogens topic, we've got steamy or misty fumes of our hydrogen bromide, and this is a very vigorous reaction. Okay, so write those in your observations section. So just a little note at the bottom says that we don't usually use this method. We normally do it the previous way because we don't get very good yields with this method. Okay, the next method is very similar. Again, we take our corresponding alcohol, and instead of using phosphorus pentabromide, we now use phosphorus tribromide. Okay, so again, sticking with our bromobutane example, we take our corresponding alcohol, which is butanol, plus our PBr3, which react to give us our bromobutane, plus phosphorus acid. Notice it's not phosphoric acid, it's phosphorus acid. Okay, and to balance that, obviously we've used 3 bromides here, and so I need a 3 in front of this, and I balance that by putting a 3 in front of here. Okay, and our observations are quite simple this time. Where phosphorus pentabromide was a yellow solid, phosphorus tribromide is a colourless, pungent liquid. Okay, and again, your note there at the bottom that we don't usually use this method because it gives us poor yields as well. Okay, moving on to our next method is preparing our chloroalkanes from something called thionyl chloride. Thionyl chloride is something that looks like this. It's got sulfur, double bonded to an oxygen with 2 chlorines sticking off the end. Okay, so that's thionyl chloride. We add that again to the corresponding alcohol, and we get our chloroalkane. So in this case, we're going to use ethanol. So it's going to be ethanol. We're going to be producing the corresponding chloroalkane, which is obviously chloroethane. Remember, we don't need our positional or our locant number because it doesn't matter which carbon it's on. You can number them both as 1. So our ethanol plus our thionyl chloride gives us chloroethane plus sulfur dioxide plus hydrochloric acid. Now, this is going to be looked at in closer detail in Unit 1.6, which is our next topic, the reaction of alcohols. This method slightly better than the last two. Obviously we've looked at the chloro example here, so our alternative would be phosphorus pentachloride rather than pentabromide. But this method gives us a higher yield. But again, the first method is still our preference. Okay, and lastly, there's just two more to look at, and we have already looked at these methods from previous topics. So one from our alkanes topic and one from our alkenes. Okay, so if you think about our reaction of chloromethane, producing chloromethane from methane and chlorine, okay, and this is the one that we have to do in the presence of UV light. Okay, so our equation is, our overall equation is methane plus our chlorine gives us chloroethane plus hydrogen chloride. Okay, and the mechanism, I want you to think, what is the name of the mechanism that we use to get chloromethane from methane and chlorine? So I want you to have a think about what the mechanism is and fill it in here, and then I'll check that with you on Monday. And then another reaction we've already seen is the reaction of alkenes and a hydrogen halide. So if you remember, our alkenes are our unsaturated compounds, and so we can add compounds across the double bond. Okay, we can add electrophiles across the double bond. Okay, and for example, we're going to look at ethene reacting with hydrogen chloride to give us chloroethane. So we've got ethene plus our hydrochloric acid, or hydrogen chloride rather, reacting to give us, it just adds across the double bond, and so it's C2H5Cl. Okay, and again, I want you to have a think about what the name of that mechanism is. Just to recap on that, your mechanism should look like this. You remember, there's our ethene. This is something you should be very confident in drawing now. And our hydrogen chloride is our electrophile. Hydrogen is delta plus. Chlorine is delta negative because of our dipole. A pair of electrons from the double bond come out, attack the delta plus hydrogen end of our hydrogen chloride. That bond has to then break because hydrogen can only have one bond, and so the pair of electrons go fully to the chlorine. And that gives us so our hydrogen has now added on, formed a bond with that carbon. This carbon on the right, the one I'm colouring in green, it's lost a share of electrons, and so it has a delta positive charge. our chlorine has a delta negative charge because it's been given an extra share of electrons. Okay, so it comes in and attacks that carbon. And we end up with hydrogen chloride has added across the double bond. And so now we've got chloroethane. So what is the name of that type of mechanism? So have a think and fill it in at the bottom of page 11. If that's not a mechanism you're familiar with, please go back to the alkenes topic. The same with method number 5 from your method of preparing your chloromethane from methane and chlorine. If that's something you're not familiar with, you need to go back to your alkanes topic. These are mechanisms you need to be familiar with. You need to be familiar with how to draw them and what the name of the overall mechanism is. So fill that in bottom of page 11, and that's us then finished with how we prepare halogenoalkanes.